So what we did was for the reaction, methane combustion. We had the energy went down. In fact, delta H. What was delta H equal to? Calculate. Do you have that in your notes, or did anybody write it down? Oh, okay. Okay. Thanks. Negative 890.29 kilojoules. The delta S. This is for 1 mole. Delta S.
Negative 242.98.
Okay. Since this is for 1 mole, typically we have kilojoules per mole and joules per mole Kelvin. We're just combusting 1 mole methane. And so, actually the entropy is not favorable. The entropy goes down. And so this is favorable, this is not favorable. And so we don't know which one. Actually, we do know which one because we know that combustion of methane is favorable. And so it looks like energy wins out in this case, but that's not always true. Sometimes entropy wins out. Sometimes energy is unfavorable, but entropy is. And so we need some way of comparing the two. When we look at these two, the units are different here. This is joules per Kelvin, this is kilojoules. And so you might be able to think, in terms of dimensional analysis, how we can compare them. How can we make the units the same here? Well, we can convert this into kilojoules, and then we can get rid of the Kelvin. But how can we get rid of the Kelvin? We can get rid of the Kelvin by multiplying it by temperature in Kelvin, 298 Kelvin. And so maybe then that would be a more fair comparison. So let's go ahead and compare that. Because I know the temperature of appendix D data, the temperature is 298.15. So I'll just go ahead and do the 242. What was it, 242.29? Did I hear that? 0.98. Okay, 242.98. 242.98. And the temperature that our data was is 298.15. Which gives me, at 298 Kelvin, if I just take these two and multiply together, I'm going to get minus 72,444 joules, which is equal to minus 72.4 kilojoules, 0.44 kilojoules. Is that okay to do? Can I just go ahead and multiply by temperature? Well, a lot of the temperature is correct because that's the correct temperature, and so a lot of equations that we get are just derived, from dimensional analysis, just trying to work out the units. And so, if we could do this now, let's compare the two numbers. Which number is larger? Now, I asked you which number is smaller as far as entropy goes. So when we're looking at entropy, we want the lower entropy, right? And so minus 8, or temperature. If we're looking at temperature, we want the lower temperature. So let's do like minus 8 degrees C is a lower temperature than 0 degrees C, right? But when we're looking at energy, there's no such thing. Actually, there's no such thing as negative temperatures, unless, well, there is. I guess Celsius and Fahrenheit, we have negative temperatures. But is there such thing as a negative, is there such thing as a negative energy? And it depends on how you look at temperature and energy. If you look at temperature as being kinetic energy and motion, is there such thing as negative motion versus positive motion? Well, motion's motion. And the negative and positive just because you came up with some arbitrary point of reference. And just like energy, there's no such thing as negative I mean, if somebody asks you, you know, I'd like negative 200 joules worth of energy, can they give it to you? You know, no. What they can do is they can take 200 joules of energy from you. If they take 200 joules of energy from you, then you've lost it, and so we say, oh, it's negative 200 joules. And so which of these two numbers is larger? Minus 890 or minus 72? I heard two different answers. Minus 72 is larger? Okay, this is it. Okay, I'm going to give you a choice. I'm going to take $72 from you, or I'm going to take $890 from you. Which one would be larger or smaller? Well, which one would be larger? Would $72, minus $72 be larger than minus $890? Did you say that? And so I don't think minus 72 is larger. I think minus 890 is larger. That's going to be a bigger hit on your bank account. And so energy, like currency, there's no such thing as negative $20 bill. You can't give somebody. I'd like to be able to give everybody a negative $20 bill, and then I'll just collect all the $20 bills here, you know? But unfortunately, there's no such thing. And so the same thing with energy. The negative and the positive sign is just to tell you, you know, which direction. Is the system losing or the system gaining? You know? Just like you would for your bank account, you know, minus $20. Means you lost $20 out of your account. And so here, which one's larger? This is larger. And so in a sense, maybe this is the way we compare it, but maybe not. And this is it. But you know, this is unfavorable. If you think about this, this is unfavorable by about 72, because what we want is we want entropy not to be negative. We want entropy to be positive. We want entropy to go up. Right? Here it's going down, but it's going down about 72 kilojoules worth. And this is this we want negative, and so this is what we're looking for. And so this is one way of comparing it. But is that correct? Is that the correct way to just compare the energies and see which one is dominant? And it turns out, yeah, that is correct. That's correct because when we look at these chemical reactions, we have something called the second law of thermodynamics. And so let's talk about that. Second law. And it turns out for all spontaneous processes, spontaneous being a reaction with some driving force, those are spontaneous. If there's no driving force, they're non-spontaneous. And so all spontaneous reactions and processes have something in common. Do you know what they all have in common? What all spontaneous reactions and processes have in common is that we see that delta S of the universe increases greater than 0. If delta S of the universe increases, then we know it should be spontaneous. And so if I have to look at delta S of the universe, then, you know, appendix D is too small because I need everything in the universe to be in appendix D so I can calculate the entropy before and the entropy after to see if that change should be spontaneous, right? And so it's too much. It's too much to measure. And then also, how did this observation come about? This observation, you know, this is based on observations. In fact, thermodynamics is all based on observations. Thermodynamics came before, you know, atomic theory. And these observations, you know, people have been trying to find violations of the laws of thermodynamics for over 100 years, but nobody's been successful. So the second law holds, first law holds, third law. So delta S of the universe is greater than 0, but that's a bit too much, so we have to break this down. The universe can be broken down into what? We do this. We did this in chapter 7. We break down the universe into two things. What? the system and the surroundings. And so what we could say is this: we could say that delta S of the system plus delta S of the surroundings has to increase. So it turns out that the system, the system entropy can increase, and the surroundings can decrease. I mean, it still could be spontaneous. It could be spontaneous if the system increases more than the surroundings decreases, or vice versa. And so this is still a bit much, for us. And so we have to think if we can surround. The system's no problem. We just did that. When we calculated this delta S is for the reaction. And the reaction is what we call the system here. And so the delta S of the system is usually no problem because in appendix D, that usually gives it to us. But the surroundings is a bit more of a problem because appendix D is not going to have everything else in the universe in there. And so the surroundings, well, it turns out that with thermodynamics, and this is what you do with thermodynamics. If you look at the first part of chapter 13, you see lots of equations, right? With lots of equations like that, what you do is you have to understand those, and you have to figure out the relationships between those so that you can relate one thing to another thing. And so here, with delta S of the surroundings, and this is an equation you don't necessarily have to memorize, but if we have delta S of the system here, then we can relate the delta S of the surroundings. Delta S of the surroundings is also equal to Q over T. Q reversible over T. Now, that was an equation that was up there earlier, but this is going to be Q of the surroundings. This should be greater than 0. Well, from the first law of thermodynamics, what does the first law of thermodynamics tell us? The first law of thermodynamics tells us that energy is conserved. That energy is neither created nor destroyed. So what that means is the energy content of the universe is fixed. There's a fixed amount of energy in the universe. And we can transfer that energy between the system and the surroundings, basically, but the total energy is going to be the same. Now, what about the entropy? Is the entropy of the universe fixed? The entropy of the universe is not fixed. So, for example, in the first law, you would understand that the Q of the surroundings. Well, if the surroundings absorbs or releases heat, it's got to go somewhere. Where does that heat go? The kinetic energy. Heat is the transfer of kinetic energy from higher to lower. Well, if the surroundings absorbs heat, where did that heat come from? The system. If the surroundings loses heat, where does the heat go? Into the system. The heat just doesn't disappear. And so what we know is that Q of the system is equal to minus Q of the surroundings. In other words, this is the first law of thermodynamics here stated in a different way. Any heat gained or lost by the system is heat lost or gained by the surroundings. It's from the first law. Can we say the same thing about entropy? So delta S of the system is equal to minus delta S of the surroundings? Is entropy conserved? No, entropy is not. Entropy is increasing. Once the entropy of the universe stops increasing, then there's no driving force for change, basically. Once the entropy of the universe has been maximized, well, how do you maximize the entropy of the universe? Well, everything has to be broken apart, right? And scattered, randomized, all the atoms. There would be nothing left. Everything would be homogeneous in a way. But anyway, we go back to this. So what we can say is that delta S of the system delta S of the system, which we can calculate from appendix D, is delta S of the system plus a minus Q of the system over T is greater than 0. What's the definition of enthalpy? Actually, let me not ask you that. Did you guys review enthalpy? What are the restrictions on enthalpy? Constant pressure. And so what we do is we just say, okay, we're going to fix it to constant pressure. There's one more restriction. What's the second restriction on enthalpy that we're going to do? And what is enthalpy? Somebody just tell me briefly what enthalpy is. Tell me in terms of path dependent and state functions what enthalpy is. All right. Did you review and it just didn't click, or did you not review enthalpy? Did you review enthalpy or not review enthalpy? Well, you know, pretty soon, yeah. I asked you to review chapter 7, but and then pretty soon I'm not going to have time to go back and review any Chem 1A stuff. We're just going to move, and I'm going to expect if it didn't click, just go back and review it on your own. But I can't keep going back to the Chem 1A stuff because of time, unfortunately. But during office, there's no problem. During office, you can come and I'll talk to you about enthalpy. But enthalpy, Q, is Q path dependent or a state function? Q. Q is a path-dependent function. So yesterday I asked you, if I burn a mole of methane in a bomb versus burn a mole of methane, this is the same amount of methane. If I burn a mole of methane in the open lab, am I going to get the same amount of heat or different amount of heat? And I think everybody said different amount of heat, right? But I always want the same amount of heat. Otherwise, I can't do any calculations. If I'm always getting a different amount of heat, depending on how I do it, right? Then how can I calculate how much methane is required to heat up a pot of water? Well, it depends. Am I getting this much heat, that much heat, this much heat, And so the only way to do calculations is to force Q to become a state function. And the way we do that is we place two restrictions on Q. One is constant pressure, two is what? If we place this second restriction, then we're always going to get the same amount of heat when we burn a mole of methane. Therefore, we can do a simple calculation. How many liters of methane would be required to heat 1,000 grams of water from 0 to 100 degrees C or something like that, or 25 to 100 degrees C, right? And so what was the second restriction? No, constant volume, we can't have both. We can't have constant pressure and constant volume. That just doesn't work. We have two universes in chemistry. We have the constant pressure in thermodynamics. We have the constant pressure, and so if we're in constant pressure, we're always thinking constant pressure, or we have constant, not temperature. We don't have constant temperature because it depends on if we're looking at an object or reaction or process. I started this off with the gases. When we visualize air in this room, we could visualize it either in the constant volume universe or in the constant pressure universe. And so when we visualize this, the air in this room, if I have a liter of air, am I looking at that liter from the perspective of constant volume, or am I looking at that liter in the perspective of constant pressure? Do you recall that one? Well, now we're looking at it in terms of constant pressure, right? And so constant pressure and constant volume are two totally different perspectives, and you use different thermodynamic calculations depending on if you're approaching things constant pressure versus constant volume. That's one of the first things you look at, and so that's why we were talking about gases and visualizing air as a constant pressure mixture or a constant volume mixture. And so when you start to visualize that, then you go, okay, I'm going to go through this series of equations here. If I'm in the constant volume universe, I'm going to use delta U. I'm not going to use delta H. Delta H would be totally meaningless if I'm doing constant volume, unless they so happen to be equal. When is delta U and delta H equal? And this is why you need to know the second restriction, because if you don't know the second restriction, then you have no idea when they're equal and when they're not equal. It's probably safe just to say they're not equal, and then just do the calculation and see. But if you know this, then you could tell, it's equal or not equal. So what is the second restriction? And so maybe this is it. When I said to review chapter 7, I don't mean to review this, like delta H is equal to the sum of the delta H is the formation of the products minus the sum of the delta H is the formation of the reactants. That is equation I'd even give you on a test, because the equation is not that, you can always look that up. But what if you Googled it? Can you just Google it and see? But anyway, okay, we're going to restrict to constant pressure, and then 2. We're going to restrict the work. We're only going to have P delta V work only. P delta V work only. This P delta V is called the natural work of a chemical reaction. I saw in the combustion of methane there's going to be work done because what happened was the system volume changed. If the system volume changes, under constant pressure conditions, then we have to have work done. Okay. Then Q can be made into a state function. Q is defined as delta H. The definition of delta H is Q, just the heat of the reaction part, but made into a state function, so we always get the same amount of heat. Normally Q is a path-dependent function. Also, delta H, the way I think about delta H is this. This is the way I explain it in Chem 1A. I don't know if anybody remembers this, but delta H, I think in terms of this. Delta H is going to equal delta U, well actually, let me just write it here. Delta U is equal to Q plus W. If we restrict Q, then we can call Q delta H, right? And so this is going to give us delta U is equal to delta H plus W. And so what I think of delta H is this, as a conceptual thing. If I try to visualize what's going on with delta H compared to delta U, I think in terms of this. Delta H is equal to delta U minus W. Does somebody remember this, the analogy last year? I just want to see. I'm very interested in memory stuff. So, Kelly, you remember what I said about this? What's that? Yeah. Okay. Then maybe I'll keep using that, because I'm just asking some of the students last time if they remember this. So, if the analogy is memorable or forgettable, and so if you remember it, then I'll continue. But the way I think about W is, it's either tax if the system does work. How does the system do work? The system expands. Then it's a tax. We're going to get less energy. And so what I think of this is, I think of delta H as your net pay. Delta U is your gross pay. And so let's say your gross pay is $1,000. Are you going to get $1,000 take home? No, because what's going to happen is there's going to be a tax on there. And that tax means you're going to net less, $900, let's say, instead of $1,000. Uh-huh.
So is that statement only true for the pressure volume work? Or what?
No. This is for any work here. The reason I don't write it like this, in your book it's written like this, delta U plus P delta V. I don't write it P delta V because it's actually minus a plus, minus a minus P delta V. Right? And so if I wrote it like this, delta U minus a minus P delta V, and minus P delta V is the work of the system, then it's okay. But I just leave it as work because then when I think about work, I'm only thinking about one type of work because this is a restriction here. I'm not thinking about electrical work or whatever else that we can do when we have delta H. But you know, other types of work can be done. We just add additional taxes to this. Anyway, we'll go back here, but the way we add the additional taxes is not here. For delta H, it is only P delta V work. And so what we do is we take that delta H. Let's say you ate a 1,000-calorie candy bar. I ate a 1,000-calorie candy bar or something like that, right? That gives me a delta H of this many calories, 1,000 calories. Does that mean, you know, delta H is heat? Does that mean all that 1,000 calories just goes into warming up my body? No, what you can do with that 1,000 calories is you can convert some of that into work. And so if you have additional work, what we do is we take our 1,000 calories that we got from that candy bar and then start subtracting the work of walking around. You know, this is mechanical work or, you know, whatever. You start subtracting all the works from here. And the rest is given off as heat. And so what I do is this is the net pay, this is your usable energy. Whether you keep it as heat or you convert it into work, up to you. Just because it's called heat here doesn't mean it stays heat. Now the tricky thing is this. Actually, I said I wasn't going to go back through this. We'll do this. Okay, this is a delta U here. If I'm looking at delta U and I'm looking at methane combustion, then remember what happened to the volume. What happened to the volume here? The volume decreased. That means if the volume decreases, that means the surroundings does the work. And so what happens is the surroundings loses energy, the system gains energy due to the surroundings doing the work. And then delta U is Q plus W. And so this will be Q. But if we do this under constant pressure conditions, this is delta H. And the work that's done is just P delta V work. And so I asked you the other day, are you going to get more energy burning in the bomb? If we burn it in the bomb, we get delta U. If we burn it in the open lab, we're going to get delta H. Delta H is bigger than delta U. It's a bigger drop in energy. It's going to release more energy to the surroundings. Now, this doesn't have to be. You know, for example, we can, when we think about heat, some people get confused because people think that this has got to stay heat. And some people think that first you release the heat and then you do the work. And so one student one semester, I had a difficult time trying to explain this to that particular student, but that particular student thought that, you know, if you eat 1,000-calorie candy bar, that 1,000-calorie candy bar is converted into heat, 1,000 calories, and then you use that heat like a steam engine. You know, a steam engine, you heat up the water, it creates steam, and then you get mechanical work done from that. And so they thought of this as happening stepwise. You burn you burn the candy bar, let's say, in your body, metabolize it. You create heat, and then you use that heat to power your machinery, like, you know, little steam engines you have, you know, for your muscles. Is that the case? And so they're telling me about the Carnot cycle. They're telling me about heat efficiencies of steam engines. all this stuff, but that's not what I'm talking. What we're talking about is, you don't have to go to heat here. I could take this heat and then start doing other work with this. This would be all heat if I didn't do other work. And so what I'm doing here, and this is what I was trying to explain, we don't have to convert that into heat. We can convert that straight into work. So we're going from potential energy into work rather than potential energy into heat and then into work. Does it make sense at all or not? In other words, this. Actually, this is kind of similar to the question you were asking the other day. The question you're asking the other day is about, let's say if I had H2O solid at 0 degrees C. Did I already talk about this? No. If I had H2O solid at 0 degrees C and I add heat to this, what's going to happen? It's going to melt. It's going to melt, but is it going to get hot? No, the first step is we have to melt all the ice, and the ice is going to stay at 0 degrees C. And so here, all that heat is being converted straight into potential energy, right? Well, this person would think, okay, the heat's got to be heated, and then it's going to be converted in the heat engine, or something like this. No, that doesn't happen. We're going straight into potential. And the same thing here. We can go straight from potential energy into work. This is work. This is what I call unavoidable. This is why I call it a tax. Can you avoid the system expanding or contracting? Absolutely not. You can't avoid this because of the way we visualize gases. The way we visualize gases is we have to use Avogadro's. Avogadro says the pressure stays constant and the volumes have to grow or shrink depending on how many moles of gas you have. And so when we're always thinking Avogadro's, then the volume has to change in order to accommodate fewer or larger. And so I asked you earlier, when is delta H and delta U the same? When delta H and delta U are the same is when the moles of gas, when the initial moles of gas and the final moles of gas, it's not just moles of gas. In Petrucci they say moles of gas because they ignore liquids and solids. If liquids and solids are very small, so they say it's small, so we'll just ignore it. But in reality, it's when the initial volume and the final volume are exactly the same, and then there's no work done, then delta U and delta H are the same. Uh-huh.
When you melt solid ice, does the energy go into the entropy of liquid?
No, the energy goes into breaking hydrogen bonds. It costs you energy to break the hydrogen bonds. When you form the hydrogen bonds, it releases energy. So this is not hot. When we freeze ice, when we freeze water, right? When we freeze water, we're removing heat.
Yeah.
Heat, when people think about heat, they think kinetic energy, right? But when you look at the kinetic energy initial versus the kinetic energy final, is there any difference in the kinetic energy? No. And so this is it. This is converting potential energy straight into heat. Well, we could do the same thing. We can convert potential energy straight into work. We don't have to go through some heat engine, people who know physics or whatever else, heat engine cycle. We're just going straight into. And so, actually, I'm getting sidetracked here. I didn't want to talk too much about that, but here, it's not like this is vibrating much faster. It's just, we don't have the hydrogen bonds optimized. Once we get the hydrogen bonds optimized, then it's more stable. It releases the energy as heat. This is actually, I was going to talk about this a little bit. We looked at one type of entropy, actually. The one type of entropy we looked at is positional entropy. How many different, like the library. Did I talk about the library yesterday? The New York Library? Okay. Another analogy of thinking about entropy is like this. Because I was listening to the radio the other day, and they're talking about the New York Library, and how it was organized and all this stuff, impressive thing. And so And then they mentioned something like, if you dump 10,000 books on the floor, is that a library? No, if you dump 10,000 books on the floor and then start placing those on the shelves, if you start placing those on the shelves randomly, right, we have a high entropy because each position on the shelves can have one of 10,000 books. And this entropy is going to be very high, right? But what they said is how well organized it is. So all of a sudden you start putting constraints like this book has to be here. And then I thought about the extreme. Is it possible that there's some librarian out there who, the book has to be perfectly aligned, to the nearest millimeter. And so, you're thinking about it. Okay, now that book is in the perfect position. And then I was thinking, if they had each book in a perfect position, then that would be a perfect library. And if we had a perfect library, the entropy would be 0 because each book would be precisely in the correct place, right? And then it would be completely constrained. Well, how long would it last at 0 entropy? Not very long, because pretty soon people are going to start messing with the books, right? Well, that's called positional entropy. We also have one other type of energy. We have, entropy. We have energy entropy. And so if we think about energy entropy, what do you think? Is heat, because these are two things here. Here, this is potential energy. And that potential energy can be used to do work or it can be used to create heat. Actually, I should go to methane here. This potential energy can be used to do work or it can be used to create heat. Well, if we do work, it has a different entropy than if we do heat. Which one do you think? Like, say, for example, there are cars going around, and they were thinking about using methane as a fuel cell. And so if I convert this potential energy into electrical energy, then, let's say I convert this potential energy into electrical energy versus converting this potential energy into heat, is there a difference in the entropy of electrical energy versus the different, a difference in entropy in electrical energy versus heat? Which one do you think is more ordered, more structured? Do you think electrical energy or heat? Electrical energy. So electrical energy has a lower entropy than heat. In fact, heat has a kind of a high entropy because the heat just disperses everywhere. Which one do you think is a more usable form of energy? Electrical energy or heat? Which one do you think you can do more stuff with? Which one has more potential? For like driving force for change? Electrical or heat? Well, it turns out electrical, electrical with electrical energy, you can convert that electrical energy into mechanical energy, or you can convert it into heat. Different things. You could do the same thing with heat, but converting heat into mechanical work is terribly inefficient. It turns out, steam engines aren't very efficient. And so people are looking at powering cars with electricity versus a steam, like the old locomotives, all that kind of stuff. But anyway, we need to talk about that because, let me continue with this over here. And so, when I ask you to review Chapter 7, these are the kind of things you want to think about, when you're reviewing Chapter 7, the conceptual stuff. Do you understand the conceptual stuff about the delta H, delta U, heat, work, system, surroundings, that kind of stuff? Oh, well, let me continue here. Delta H is equal to delta U minus W. W, if the system volume, actually, let's see. If delta V of the system is greater than 0, then the system has to do work, and it's going to be a tax. This is for exothermic or yeah, exo. We have endothermic. We have 6 scenarios for this. If delta V of the system is about equal to 0, then there's no tax. You don't have to worry about it. Delta U and delta H are going to do the same thing. It goes to 0. If delta V of the system is less than 0, then we get a bonus. And so this is what we have here. Delta V of the system, this is 75 liters going to about 25 liters. We lost 50 liters. If you guys remember, how much energy is that? Roughly. Just give me a guesstimate. How much energy? If we lose 50 liters, about how much energy is that? Well, you guys might remember this from chapter 7. If we take 8.314 joules per mole Kelvin and divide that by 0.08206 liters atmosphere per mole Kelvin. And so we take R divided by R, right? R divided by R. What do we get? We get 101.3. Actually, let's just go. We'll go with 101.3 joules per liter atmosphere. So in other words, the way I visualize this number is I blow up a 1 liter balloon. If I blow up a 1 liter balloon against the pressure of 1 atmosphere, how much energy am I going to spend? I'm going to expend 100 joules. It's going to cost me 100 joules to blow up a 1 liter balloon. A 2 liter balloon, 200 joules. A 3 liter balloon, 300 joules. Now, if I go deep underwater and I try to blow it up under high pressure, let's say go 2 atmospheres, it's going to cost me twice as much energy. Right? And so this is the way I visualize this number. You know, sometimes this is what I try to do in trying to memorize things. You know, try to memorize this. And so we can convert. These are conversions that you do in chapter 7. And so here, you know, this is why I do this. This is why I say this is about 75 liters. This is about 25 liters. So I see that's going to be a 50 liter drop. That's going to cost me 50 times 100 would be 50 or 5,000 joules or 5 kilojoules. That's just 5 kilojoules of work, right? But who did the work? Who did the work? The surrounding. The surroundings did about 5 kilojoules of work. That means the system gained 5 kilojoules of work. That means this. If I do this under constant pressure conditions, I'm going to get minus 890, was that it? Kilojoules. If I do this under constant volume conditions, I'm not going to get this much. I'm only going to get minus 885 kilojoules worth of work. Does that make sense? Because I get a 5 kilojoule bonus from this is just a guesstimate. The reason I do guesstimates is this. Let me tell you, some of you are planning to take standardized tests, correct? Like the, whatever, MCAT or whatever else. If you have to sit there and plug away on your calculator, there's no way you're going to finish that test. Even if you don't plug it away on the calculator, it's hard to finish the test because there are too many problems. And so some of the problems you can do quickly, you know, by just kind of guesstimating, you know, and this is my guesstimate. If I wanted a more accurate answer, I'd sit down and calculate the volumes of this, you know, to get a little bit more accuracy. But oftentimes you don't have to do it because they're multiple choice. Not that we always do this, you know, for multiple choice. Not that every question is multiple choice, but some things you just don't want to sit and calculate. Some things you just kind of want to guess, estimate. And so something like this we could guesstimate. And it's not hard because we know the molar, you know, if I had memorized 22.4 liters, I told you 22.4 liters is totally useless. But if you remember, what was it, Paul? You remember the number. What's the molar volume of the gas? 20, what? 22.4? Oh, okay, I thought you're the one who told me. The other one. 24.5. 24.5 is just so much easier and so much more useful. You know, I use that all the time to do, you know, rough calculations. But and so what we did was here, delta V of the system is less than 0. We lost 50 liters, so we got a little bonus. The little bonus is if we lose 50 liters against 1 atmosphere, that's 5,000 joules. So we got a 5 kilojoule bonus in energy. And so if we burn methane, a mole of methane at constant pressure, we're going to get 890 kilojoules. If we burn methane under constant volume, we can't have volume changes, therefore there's no work done. We're going to get 885 kilojoules roughly in the bomb. So there's a different amount of energy. Is it all that different? No, it's not a huge amount. But it's a little bit. Okay. And so we got a little bonus from the surroundings. All right, this is just aside stuff here. We've got to go back. This, I told you when I took thermo, I had to go back and review because I didn't know this. I didn't know any of this. All I could do was I could do this calculation, no problem. When I took thermo, I could do this. Delta H is equal to the sum of delta H of the formation of the product minus the sum of the delta H of the formation of the reactant. How valuable was that? That was kind of worthless. Anybody could do that calculation, and therefore it wasn't so important. What was much more important was the stuff that, all this stuff. And so I had to go back through all this stuff from the very beginning. Because like it had even been longer because I didn't have this stuff. And, I took it in general chem. When I took thermo, it was much longer than a summer. It was much longer than a year break, I forgot everything, totally. Actually, I didn't forget everything. I never learned it in the first place. So this is what makes thermo. If you learn all the stuff from the very beginning, then it's not that hard. If you know all this, the definitions and the relationships. Well, thermo's still hard, but it's a lot easier than what it would be if you didn't know any of this. And so this is why my thermal class, these are all chem majors. My thermal class started with about 20 students. No, maybe about 24 students. My thermal class started with 24 students. At the end, I think there were 10 students left. All chem majors. They all ended up dropping the class. Well, anyway, here, what were we talking? So what we're going to do is we're going to use this, the definition of delta H to plug it in here. And so delta S of the system, so if we have these two restrictions, and we can say this, delta S of the system plus a minus delta H of the system over T is greater than 0. And then what we're going to do, and we're going to multiply both sides times T. In fact, we'll multiply both sides by negative T. And so we'll end up with this, negative T delta S of the system. Okay, so negative T times that is going to give us plus delta H of the system is going to be greater than 0. Okay. Did I miss something? Oh yeah, I did. I did miss something. This is what I missed. Delta S of the surroundings is equal to this. And we want this to be greater than 0. And so delta S of the surroundings is equal to this. And so here, just continue. Delta S of the surroundings, sorry, I should have put that in there, is equal to this. And so when I multiply by negative T, I'm changing this also. And so I need to multiply this side by negative T as well. So this is going to be negative T times delta S of the surroundings. And I'm going to flip these around. So this is going to be delta H of the system minus T delta S of the system. And this is minus T delta S of the surroundings. And if I multiply by negative T, I also screwed something else up. You know what I screwed up? And so I'm multiplying by negative. And so I screwed something up. And what I screwed up was this. Because if I multiply by negative, that's going to change the sign here, which means that's going to change the sign on this. And I should have flipped this around. This, if I multiply by negative T, this should be less than 0 now, because now it's opposite sign. And so this should be less than 0. And so if the surroundings, not the surroundings, the universe, shoot, how do I do this? This is not the surroundings. Did I write surroundings? Sorry. This is not delta S of the surroundings, this is delta S of the universe. One more correction. This is the delta S of the universe. And delta S of the universe. So if the entropy of the universe increases, delta S of the universe increases, this whole thing's going to be negative, and so this is why we want to go. If delta S of the universe decreases, then negative times negative gives us a positive, and that's not favorable. So we want to go more negative now. Well, you know, minus T delta S of the universe is why do we do that? Why we do that is, I don't know. Maybe this equation is a little easier to look at, and that's the reason why. But what we're going to do is we're going to call this a new state function. The new state function is delta G, the change in the Gibbs free energy. And so when we're looking at delta G here, delta G encompasses the delta S of the universe here, and that's equal to delta H of the system minus T delta S of the system. And this should be less than 0. So it looks like there are two driving forces in nature. The two driving forces in nature here are this. We want the system energy to go down or up. We want it to go down. We want this to be negative. And so we want the delta H of the system to go down. What about delta S of the system? We want that to go up. And that would make this more negative. If this is negative and we make this more positive, that makes this, and that makes it more spontaneous. This is more spontaneous. But in reality, this is just one driving force. The one driving force is this. We want the entropy of the universe to go up. Okay, if we look at delta S of the system is called the positional entropy. Delta H of the system is the heat. Now, if that's the heat released, is heat a high entropy form of, or low entropy form of energy? It's a higher entropy form. You know, it's more dispersed. We can't use it as well. And so if this reaction releases a lot of heat, then it's converting potential energy into heat. If it converts potential energy is much more usable because we could go straight from potential energy into work. You know, here rather than going straight from potential energy into heat. So the more heat we dump into the surroundings, the higher the entropy will go up. Right? The more heat you dump, the higher the entropy. And so that's the second law of thermodynamics. The second law of thermodynamics is this. The more heat we dump into the surroundings from the system, the entropy will go up, and the more positional disorder, that is delta S of the system, goes up, the higher the entropy. So this is spontaneous here. Now, this gives us a direct way to mathematically compare the two. And all we're doing is we're seeing, which one dominates, which term. And we multiply by temperature here to get rid of the kelvins. The units have to be the same, like kilojoules or whatever else. And so here's a little video on this. On the second law of thermodynamics.
This is the aftermath of a natural disaster. Not natural in the usual sense, outside of human intervention, but natural because the chemical reactions that started this inferno occurred naturally and spontaneously. Workers are loading bags of ammonium nitrate fertilizer on a grain train at Texas City. They noticed that the bags were getting warm. Ammonium nitrate...
I thought they had fixed this during the break.
As the workmen had
Wasn't
noticed,
fixed.
the fire mixed
Okay. Some technical difficulties, so we'll move on from that. But this is the second law written in a different form. So this is one form of the second law here, and this is another form of the second law. Delta G is equal to delta H of the system minus T delta S of the system. Delta H of the system and delta S of the system, we can get this from Appendix D. It's the easiest way to determine it. And we're going to have different scenarios. If we look at delta H here and delta S here, we'll see. If delta H goes down and delta S goes up, then this is spontaneous. Always spontaneous. If delta H goes up and the entropy goes down, this is always non-spontaneous. When there's a conflict, let's say delta H goes down and delta S goes down, then we have a conflict. Delta H is favorable, delta S is unfavorable. And so to minimize the delta S term, we can lower the temperature. If we lower the temperature, then we say that this is non-spontaneous at high temperature, non-spontaneous at high temperature, but spontaneous at low temperature. And so we can minimize the entropy term by lowering the temperature. Okay, if on the other hand the entropy term is favorable but the energy is not, so let's say the energy goes up and the entropy goes up. And so the energy is saying no, entropy is saying yes, we can maximize the entropy by increasing the temperature here. And so this is spontaneous at high temperature, non-spontaneous at low temperature. And so do some calculations here. C. One of the first calculations we'll do is just the combustion of methane. If I combust methane, a mole of it, let's calculate our delta G. Delta G is equal to delta H, which was minus 890.29. I erased it. Wasn't paying attention too much. Minus 890.29 kilojoules. Minus T, the temperature is going to be 298 Kelvin. And what was the entropy? Delta F.
It's 242.98.
Negative 214.98.
No, negative 242.98.
242.98 joules.
Joules.
All right. Thanks. Per Kelvin. So we're going to have to convert one of these into the other unit, and so we can convert kilojoules into joules, or we convert joules into kilojoules. Usually delta G is in terms of kilojoules. And this is the typical size. So what we're going to do here is we're just going to convert that into kilojoules. So 1 kilojoule is 1,000 joules. Let's go ahead and do this calculation and see what it comes down to. We had 298. I could go 298.15 since I have more digits here. 5 times 242.98 divided by 1,000. And so the entropy term is minus 72.44 kilojoules. The energy term is minus 890.29 kilojoules here. Okay, it's a minus, So a minus, that's not favorable because that's going to give us a plus. And so we end up with minus 890.29 kilojoules. That's good. Plus 72.44 kilojoules. That's not good. But it's not big enough to prevent this from happening because it's going to come out to minus 817. Actually, I screwed up my calculation, but does somebody have it? Minus 817.5 or 0.6? Just do 0.6 kilojoules. And so this is less than 0, so it's spontaneous. Minus 817. And so this is how we can quantitate the driving force. Quantitate the driving force. And so we should see what the delta G's are quantitate. A minus 800 kilojoules, this is a strong driving force. And it's good. We'll see some numbers as we go along. Okay, let's do another calculation here. Okay, the next calculation we're going to do is H2O solid to H2O liquid. If we go H2O solid to H2O liquid, then if we want to figure out what the driving force for this is quantitatively, then we'll calculate our delta G. Delta G is going to equal delta H minus T delta S. And so we'll need to calculate delta H first. Let's go delta H. In order to get delta H, we need to know the enthalpies, standard enthalpies of formation of the products minus the reactants. So we're going to go H2O liquid minus H2O solid. That is. And so we want the appendix D. It's hard to read here, but H2O liquid minus 285.8. H2O solid. H2O solid is not there. Why is that? Because the data for this table is at 298. Is there much H2O solid at 298? No. That's not going to be a stable phase of water. And so if we want to do this, we probably have to do it at 0 degrees. We need the data at 0 degrees or lower, right? But H2O solid's not there. But take a look, H2O gas is there. Is that right? Because at 298, does water boil? No, at 298 water doesn't boil, but at 298 water will evaporate. And so at 298 Kelvin, we'll have a dynamic equilibrium, which causes vapor pressure. And so here we'll have some liquid water, H2O liquid. If I look at H2O liquid at 25 degrees C, are all the molecules moving with the same energy? Do all the molecules have the same energy at 25 degrees C for water? And so let's say I have a mole of water, 18 milliliters. All 6.022 times 10 to the 23rd molecules have exactly the same energy. That is 25 degrees C. Yes? No. The answer is no. Not all water molecules will have the same energy. In fact, we'll see a distribution of energies. What does that distribution of energies look like? What does a distribution of energies in the water molecule look like? Well, here we probably plot the population versus the energy. And what would we see? What kind of distribution is this? What's the name of this distribution? It's not a bell curve. It's a bell curve with a tail on it. So we don't call it a normal distribution, which would be bell curve, or Gaussian distribution, which is a bell curve. It gives a different name. It's not a Gaussian or a normal distribution. It's called a Boltzmann distribution. It's going to look like this. And that is, you know, if I have it, there's something called, remember URMS? URMS, the root mean square speed? Well, we're going to have that kind of thing. You know, if we average this, you know, if we gave all the water molecules the exact same energy, it would be this energy here. And if we gave, you know, if we gave, like, we cooled down the faster and the more, and we warmed up the colder, and we gave every single water molecule the exact same energy, this would be it. This is our temperature, 25 degrees C here, basically. Corresponds to that. You know, this distribution gives us a temperature of 25 degrees C. But it turns out that, do all the water molecules move with the same energy? No. There's going to be a fraction of water molecules with enough energy. This is the cutoff here. If a water molecule has an energy above this cutoff, it can escape from the surface and go into the gas phase. And so even at 25 degrees C, there's a small fraction of molecules which has enough energy to escape the surface and create what we call vapor pressure. And eventually this vapor pressure builds up here until it's saturated the space above here, because what's going to happen is these water molecules can come back and condense. And so when we have this is called an equilibrium, when we have this dynamic equilibrium where the evaporation rate is equal to the condensation rate, then we've reached a point of saturation and we have the vapor pressure of water. If we change the temperature, we're going to change the vapor pressure. So at higher temperatures, we'll have a larger vapor pressure because we're going to increase the fraction of molecules in the energy. At lower temperatures, we're going to decrease the vapor pressure because we're going to have fewer water molecules that can evaporate. And so this is going to give us a temperature greater than 25. This is a temperature less than 25. for that distribution, but not all the water molecules have the same. And so here it makes sense. You know, we have H2O liquid and we have H2O gas. Well, sure, we can have H2O gas. We're going to have some kind of equilibrium between H2O gas and H2O liquid at room temperature, 298 Kelvin. And so these are the numbers for that. And so this problem, H2O solid to H2O liquid, is not going to work at 298. What we'd have to do is we'd have to look up the data. Unfortunately, the data is not in this table because this table is only for 298. We'd have to look up the data in an alternate table, you know, at different temperatures. What we can do, however, is we can change the problem. Let's go from H2O liquid to H2O gas. Which phase is favored at room temperature? At room temperature, is the liquid phase favored or the gaseous phase favored? Yeah, by far the liquid phase is favored. And so do you expect this to be spontaneous? In a way, it seems to be spontaneous because if I spill a drop of water and come back in the afternoon, it's all evaporated, right? And so it seems like there's a driving force. It went and spontaneously evaporated completely. But what we have to do is we have to reach, you know, that's not the end point. When we're doing driving forces, we're saying, you know, where is the end point? When we're doing driving forces, we got to look, in this case, we're going to have some leftover H2O liquid and then the gas space here. And so if we go to an indoor swimming pool or something like that, then which one's the favored phase? Did all the water in the swimming pool evaporate? Like, I think we have an indoor swimming pool here, right? Will all the water, do they have to go every morning and refill the water because all the water is evaporating off? No. What's happening is we've reached this state of dynamic equilibrium, and it just goes to show you that the water, the more favored phase of water is H2O liquid. And so, well, let's take a look at what the driving force for this particular reaction is here. And so what we're going to do is we're going to calculate our delta H. When we calculate our delta H, we look at H2O final, which is minus 241.8, the gas, minus H2O initial, and so that gives us minus 44.0 kilojoules per mole. And we're only going to do 1 mole, so I'm just going to leave it as kilojoules. I'm not going to do 2 moles or whatever else. And then let's look at our delta S. These are under standard conditions. And so if we go to our delta S here, that's going to be 6991. Oh, actually, final minus initial. 188.8 minus 6991. And so that's going to be 18.89. 19.89? What is that? 118. I actually need a calculator. 188. 188.8 minus 69.91. It's that extra decimal. 118.89. And so if we look at the entropy, it's plus 118.89. That kind of makes sense. This is joules per Kelvin. That kind of makes sense because gases are about what, as far as entropy goes? Gases are about gases are about 100, 1,000, 200. Okay, gases are about 200. Liquids are about 100. And so I expect delta S for this liquid to gas to be about, going from liquid to gas should be about 200 minus 100 gives me 100. So I expect the entropy to increase by 100, liquid to gas. That's, you know, that's called a guesstimate, right? Some guy named Troughton came up with a rule, Troughton's rule. I don't know if anybody read. Did anybody read Troughton's rule? Troughton's rule tried to come up with a better guesstimate than mine. My guesstimate kind of sucks because, you know, it's just really ballpark, right? But Troughton really tried to get on top of it and give you a much better estimate based on lots of data. And so some people memorize Troughton's rule. I know at ballpark, I don't really pay too much. But sometimes you want a little bit better than a ballpark. And so let's look at Troughton's rule here. Troughton's rule says that when you go from a liquid to a gas, delta S is about 87. You know, that's a heck of a lot more precise than mine. Mine is just ballpark 100. But Troughton's rule says 87. How good is that? You know, it's not a law. If this were Troughton's law, then you'd say, oh, so that's probably pretty good. But this is a rule, so there's got to be exceptions. Right? And so how good is that? Well, you know, it's okay. It's okay for a lot of organic liquids. It works out pretty decent. Not so bad. But where does Troughton's rule fail? Troughton's rule fails when we're looking at you know, exceptionally organized liquids. All the gases are going to kind of be the same. But if the liquid is much more organized, it's going to deviate. And so let's look at this. Troughton's rule says when we go from a liquid to gas, it should be 87 joules per Kelvin. What did we just calculate for water? We just calculated 119 joules per Kelvin. You know what I want to do with Troughton's rule? I want to throw it in the trash now, because it told me Troughton's rule said it should be 87. I got 119. Why even bother? Do you think that's pretty good? Do you think that's good? No. It's pretty worthless. Unless you're dealing with organic liquids. And with organic liquids, then it comes out okay. Like, say, if you're dealing with hexane or benzene or toluene, a whole bunch of organic liquids, then it's okay. But once you start dealing with, like, water, you know, which is pretty well organized in liquid phase, methanol, ethanol, then Troughton's rule is worthless. And in the homework, though, there's a Troughton's rule type problem. In the book, you can read about Troughton's rule. But basically, that's all I'm going to say about Troughton's rule. Let's just read this. So it's a quick paragraph. Instances in which Troughton's rule fails are also understandable. In water and in ethanol, for example, hydrogen bonding among the molecules produces a lower entropy than would otherwise be expected in the liquid state. Consequently, the entropy increases in the vaporization process is greater than normal. This is the normal. And so they're saying it should be bigger than 87. Well, obviously it's bigger, it's 119. So that's Troughton's rule. All right, let's go ahead and calculate our delta G for this. Delta G is going to be the quantitative driving force. And so what do the numbers mean? We'll talk about what the numbers mean a little bit later, but let's first do our delta G. Our delta G is going to be equal to delta H, which is minus 44.0 kilojoules, minus T. T is 298.2 or 298.15. Just put that in Kelvin. Times delta S. Delta S I'm going to convert in my head to kilojoules. So I'll just move the decimal 3 over, 0.11889 kilojoules per Kelvin. And so the Kelvins cancel, that leaves me with kilojoules, and I'm going to calculate the entropy term just to see if the entropy is favorable or not. And so let's do 298.15 times 0.11889. And this entropy term comes out to, it's favorable. So it's minus 40, oops, did I get that wrong? I did. This is not minus 44. I did the calculation wrong in my head. If we go from liquid to gas, going from liquid to gas, should that be endothermic or should it be exothermic? Do you have to add heat to vaporize the water, or do you have to remove heat to vaporize water? You have to add heat, and so this was wrong. Sorry, this would be plus. That's not favorable, that's unfavorable. This is unfavorable energetically. But the entropy is favorable. And so here I have a case where the energy goes up, unfavorable, but the entropy also goes up, favorable. And so am I at a high enough temperature for this? Well, let's see, for this to happen. So this is plus 44.0 kilojoules, and this is going to be minus. So we want this minus to be big, and so how big does it come out? 35.4 sub 4. I do this sometimes. Just subscripted. I'm allowed more, but when I do the final, it's going to come out like this. So maybe I'll just leave it up. Was it enough? Was the entropy enough to overcome the energy? No. In fact, the entropy term would have to go to minus 44 to cancel out the energy term. And then it would have to go greater than minus 44, that is like a minus 45, minus 46, to turn this negative. You guys see that? And so in this case here, it's not enough. And so what we end up with is this. We end up with plus 8.5 sub 5 kilojoule. Is that favorable or unfavorable? That's unfavorable, so we call this non-spontaneous. And so what does that mean, non-spontaneous? Does it mean that water doesn't evaporate? Water will evaporate. What it means is what's favored, liquid or gas? Liquid's heavily favored. And so when we see this, well, that starts to become tricky. And this is what the numbers mean. The numbers mean like this. For methane, when I burn methane, do I have to worry about burning it all? No. As long as I have plenty of oxygen, all the methane's going to burn. And so when I have such a powerful driving force, a powerful driving force would be minus 890. That's a powerful driving force. I'm going to get complete reaction or near complete reaction. That's a strong driving force. But if I have a weaker driving force, let's say the driving force was not minus 890. Let's say the driving force was minus 8. A minus 8 driving force, what that means is the product is favored, but there's still going to be some reactant left over. And a driving force of plus 8 means that the reactants are favored. However, it's not so non-spontaneous that a little bit won't happen. And so a little bit of this does happen. I mean, we can't stop these water molecules from escaping. If they have enough energy, they're going to escape. And so when we see these numbers, we'll be able to see, more or get a better feel for how the reactions take place. Now, this is not the easiest way of figuring out this. For example, here, I want to predict this. I start off with 1 mole of water. How much will vaporize? 1/10 of a mole? Half a mole? 1/4 mole? How much will vaporize? If I start off with 1 mole of liquid water, and let's say the air is totally dry, there's 0% relative humidity, the air is totally dry, it's going to start to evaporate. Let's say, I have plenty of water so it can reach a state of dynamic equilibrium. How much of that will evaporate? So 1 mole would be 18 milliliters, 18 grams roughly. About 18 grams, how many grams will vaporize? Can you tell me that? Well, in chemistry, we want to be able to predict it. If I have 1 mole of methane and excess oxygen, how much of that methane will react? Pretty much all of it. All 24.5 liters will react. If I have 1 mole of water, liquid, how much of it will vaporize? Some of it. Well, how much? I want to know how much in grams. I don't want to know some of it, a little bit, I want a precise number. And so can I use this here to predict how much? you know, what am I going to do with this number? I got this number now. It says it's non-spontaneous, but I know a little bit will evaporate. Well, how much is that? Okay, so what's going to happen is this. When I have numbers like this, let me tell you, if I have delta G like minus 200 kilojoules and lower, actually let's go down here. Let's go to plus 200 kilojoules and then maybe 50 kilojoules and then 10 kilojoules, minus 10 kilojoules, minus 100 kilojoules, minus 200 kilojoules. You know, when I have 200 kilojoules, that's non-spontaneous. You know, pretty much these are no reaction. And if I have minus 200 and lower, that's hugely spontaneous. Like minus 890 is hugely spontaneous. Then this is about complete reaction, approximately complete reaction. But when I get into this range where the driving force is not so huge one way or the other, you know, then what I get is partial reaction. And so, you know, in Chem 1A, the types of problems that we encountered were these. We encountered reactions in which we either had no reaction or we had partial, not partial, complete reaction, right? Complete reaction. In Chem 1A. So it was easy, you know, easy to predict the stoichiometry. So if I start off with 1 mole of HCl, how much of that will hydrolyze? All of it. And so in Chem 1A, we just do the stoichiometry. In Chem 1B, we set up the stoichiometry a little different. And so if I start off with 1 mole here, and water we got plenty. So I'm going to just write a dash through water. And I have 0 moles here and 0 moles here, then no problem. I can predict because the change, which I'll call C, I'm going to lose all 1 mole of that because all of it hydrolyzes, you know, strong acids. And I'm going to gain 1 mole of this, and I'm going to gain 1 mole of this. And so at the end, this would be the end. The end is once we reach the state of dynamic equilibrium. You know, once you reach the state of dynamic equilibrium, nothing changes anymore, really. You know, things stay. And so we call that the end of the reaction. This is going to be 0 moles here, 1 mole here, and 1 mole here. That's easy. The stoichiometry is easy. I mean, you could have done this stoichiometry problem in your head, right? Why? Because the driving force is huge for this. The driving force is minus 200 plus, bigger kilojoules than that. But what if we have something like acetic acid? Acetic acid is weak acid. Do weak acids completely hydrolyze or ionize in water? No, weak acids partially hydrolyze or partially ionize in water. And so when we do the weak acid like this, we'll get H2O liquid. This is going to go to a hydronium and acetate. And what we say is this. We say that if I start off with 1 mole of acetic acid and 0 and 0 here, how much of it will hydrolyze or how much of it will ionize? Well, when I calculate my delta G, you know this is not favored. In Chem 1A, we'd say no reaction because we're going from weaker acid, acetic, to stronger acid, hydronium. Hydronium is stronger acid, therefore no reaction. But the no reaction, you know, what we could call is the anti-driving force is not so huge, you know. If this were no reaction and it was plus 200 kilojoules and above, then absolutely no reaction. But it turns out that it's not so bad. Not such that a little bit of reaction can't happen, and a little bit of reaction does happen. So how much? Well, a little bit. Well, how much is a little bit? We're going to do minus a little bit, plus a little bit, and plus a little bit. Is that how you want to do your calculation? Lose a little bit, gain a little bit. We'll have a little bit left over. Done. No, actually, that's not how we want to do our calculation. So what we got to do is, you know, when we get into scenarios like this where the driving force is not so clear cut one way or the other, you know, we can have a little bit of partial reaction occur, then we have to do a little bit more. And so this is why I need to jump ahead a little bit. And so let's take a break here, and then let me just briefly explain how we're going to jump ahead.